In this video, I'm going to show you how to apply the two models that we developed yesterday. Very briefly, I want to remind you of the models that we generated. You may remember that we examined a cart on a ramp, and we had that cart be pulled by some amount of hanging mass. Okay? If I examine the force diagram for this, I know that there's a force of gravity and there's the force that the ramp exerts up on the cart. And those are equal since the cart is at rest in the vertical direction. But there's an unbalanced force in the direction of the rope. Okay? And this caused the cart to accelerate. Okay? We collected several pieces of data and we concluded that when there is a net force acting on an object, that net force is equal to the mass of the object multiplied by its current rate of acceleration. Okay. The other thing that we saw, which we did a little bit more of, we looked at a block on a table, a little hook, and we took a spring scale to it. Okay, we added some masses to them as well, and we were trying to look at the force of friction, which we call FF. And we thought about it and we found that the force of friction is equal to a constant mu, what we call the coefficient of kinetic friction, and the normal force. And what do we mean by the normal force? Well, if I go and look at the block, here this would be the block, okay, I'm talking about and there would also be this tension force from the spring, and then the force of friction backwards, and these are equal. Okay? When I'm talking about this normal force, I'm talking about the normal force between the block and the table. Okay? Or perhaps the block and whatever material you were dragging it over at that time. The point is that we're comparing the normal force between the surface and the object that's sliding and its frictional force, and they're related through this constant, this coefficient of kinetic friction. Okay. In this first problem, we have a man in an elevator. You may have been on an elevator before, hopefully you've had it at least once, and you may have noticed that when the elevator first starts, there's a little bit of a bump. As I say, it almost feels like you're being pushed more up, right? Your knees kind of buckle maybe, or you have that sensation when it slows to a stop that you're almost being lifted up as if by magic. What you're experiencing is what we've been talking about here. You're experiencing Newton's second law. Okay? So here in this situation, the man has just gotten on the elevator, and so the elevator starts moving, meaning it accelerates. And in fact, it accelerates at a rate of 2 meters per second per second. The man has a mass of 85 kilograms. Okay. Our objective is going to be to find the force the elevator's floor, elevator, pushes up against the man. First thing, as always, let's start with the free body diagram of the man, since he's my object. Okay, well, force of gravity, he's on Earth, it's the Earth pulling down on the man, and then I've got a force between the floor and the man, right here at his feet, right? Pushes him up, or maybe doesn't push, but it definitely applies some sort of action. So I have the elevator, and that's on the man. Okay. Now right away, since he's accelerating, and he's accelerating up in a positive direction, I know now that there must also be a net force. And net force, what does that mean? Well, net force is similar to what we were doing before when we summed our forces. That is to say, one force is bigger than forces that oppose it. So here I would say that this normal force is not equal to the force of gravity. And so in a written statement, I might say that the net force will equal the normal force minus the force of gravity. Now, ordinarily, we've been looking so far at situations where it's either moving at a constant speed or is at rest, and we would say that equals 0. But now, since we're looking at a situation where the force of the floor on the man is greater than the force of gravity, we now say, well, since these are not balanced, that these two together must equal the mass of the object accelerating times the rate of the acceleration. That's what we saw in lab. This is very useful because now I can start to piece out and solve for individual forces like I did before. So here's my goal. I'm looking for him. I can start to put in some numbers here because I know some of these. For example, I know that his mass is 85 kilograms. Okay, that's easy enough. His acceleration is 2 meters per second. And you know what? I have a way to solve for the force of gravity. I know his mass, and I know that objects on Earth get pulled at 10 newtons per kilogram. So if I multiply his mass, I made that a little too small. Let me clean that up. And I can still not totally clean. And then I have a normal force. So kilograms cancel. I'm left with the amount of force that gravity is pulling on me. 85 kilograms times 2 meters per second. That's 170. And I remember that a kilogram times a meter per second is a newton. That's our definition. If you don't have that written down, you may want to write it. Anytime I have a kilogram times a meter per second, that's a newton. That's important. Now all I have to do is isolate the normal force. So 850 plus 170. So the floor of the elevator presses up on the man with 1,020 newtons, which is greater than the Earth pulls on him in the opposite direction, which was 850. This problem is on your worksheet that you're going to work on today. It's question number 2. It tells us to draw a force diagram for a 900 kilogram car that exerts 5,000 newtons of traction force on a level road. Okay, so I'll draw a picture of my situation here. I've got a car that's 900 kilograms. It's on a flat level surface. Okay. And in this problem, I want to know what's the current acceleration of the car. So I know its mass, I know it's traveling. Let's do a free body diagram for them. So they tell me I have this force of traction or thrust, whatever you want to call it, and I know already that that is equal to 5,000 newtons. So that's what the problem tells me. There will be some amount of friction, but since the problem is asking, since we're looking for acceleration, we can assume that it's accelerating in this way, thus there must be a net force in this way, in this direction, sorry. And so this force, this thrust, must be bigger than the frictional force. Oh, I forgot to mention, and this is in your notes, the coefficient of kinetic friction is 0.11. Okay? There, of course, is a force between the road and the car, and a force of gravity, and these are balanced since the car is stationary in the vertical direction. So we got a couple pieces here. I know its mass. I don't know its acceleration. So let's think through. I could go straight to the fact that the net force of an object is equal to its mass multiplied by its acceleration, but I don't know this and I don't know this. Tricky. Well, let's keep working with this for a little bit. F net can be rewritten. I know there's a net force for this horizontal direction. So let me rewrite F net in terms of individual forces of the object. There's this forward thrust, and then there's the frictional force. And that still is equal to mass times acceleration. Well, I know this. I'm not told this, but I am told the coefficient of friction. So I think, I have an expression for this. If I come over to the side here, I know that the force of friction is equal to the coefficient of friction between the object and the surface and the normal, multiplied by the normal force of that object on the surface. So if I knew this value, I could find friction, which I could put back into here and find the net force, divide by the mass, and I would have the acceleration. So I go back to my force diagram. I need this force, and I notice that it's balanced with the force of gravity. So what I could do, force of gravity in this situation is equal to the normal force. Well, hey, I know how to find the force of gravity. 10 newtons per kilogram, and the car is 900 kilograms. So therefore, that equals 9,000 newtons. So now I can find the force of friction. The force of friction would be equal to 0.11, my coefficient of friction, multiplied by 9,000 newtons. My force of friction ends up being 990 newtons. Okay. Now I can come back to my original statement here. I know the traction force, the force that the engine's pushing forward on the car. I know the force of friction, and I know the mass of the object that's accelerating, 900 kilograms. Well, now I'm pretty close to solving for my solution here. So let's see. 5,000 minus 990, that would be 4,010 newtons. That's the net force in the direction of acceleration. and I can divide that by the 900 kilograms, and that's going to be the acceleration of the object. So this car accelerates, or is accelerating, I should say, at 4.46, and I'm rounding, meters per second per second. One last note. All of these problems will be solved in the same way. Note that there are not many problems that you need to solve. There are a total of 8, including the one that I just solved in this situation. Notice that we're looking at combining the net force with our other ideas. These work similar to what we've already done in the previous unit. The difference is that when we have a net force, something that does not equal 0, it instead equals the mass of the object accelerating times its rate of acceleration.